So if I have, if my output is a 1 by n minus k vector, then the number of possibilities that I can use here is 2 to the power n minus k. So there's 2 to the power n minus k unique vectors. Minus 1 because I'm not allowed to use the all zero vector. So let's construct such an H transpose. So let's let n equals 7, and let's let k equal 4. So n minus k is 3. So the number of possible unique rows is 2 to the power of n minus k minus 1, which is 7. So I'm going to let H transpose be a 7 by 3 binary matrix. So H is going to be this. For reasons that I'll get into in a second, I'm going to put the, up here I'm going to do rows of weight 2 and 3, and down here I'm going to do rows of weight 1. So the weight 3 row is only 1, and that's it. The weight 2 rows three of those. The weight 1 rows. That's H transpose. So if H transpose is equal to that, then if H transpose is equal to that, then in principle, we should be able to correct one error. The only problem now is how do we get G? If we can't get G, then such a code does not exist. But fortunately, there's a simple recipe for getting G from H, and vice versa. So getting G from H, if H transpose can be written with some matrix P, and then an identity submatrix on the bottom. So a matrix P on top, identity submatrix on the bottom. And that's exactly what I have here. So here's my identity submatrix. By the way, P is just an arbitrary matrix, but I have to have the identity submatrix on the bottom. So that's an identity submatrix. And I'll call this P. Then G is equal to I. So how does that work? GH transpose is equal to IP times PI, which is equal to, okay, I times P. If I do this in matrix multiplication, it's IP plus PI, which is P plus P. Because it's mod 2, that's equal to what? So if I have the same matrix, and I add it mod 2 to itself, that's equal to 0. So that satisfies my criterion for G and H. GH transpose has to equal to 0, and that's exactly what happened. So in this case, I have H, which I describe as P on top and I on the bottom. Doesn't matter what P is, but I has to be the identity submatrix. Therefore, G has to equal IP, and it's important to make sure the dimensions are right. So I have 1, 2, 3, 4 rows in P and 3 columns. So let's just draw that in. the identity submatrix. Now I have 4 rows, so this is going to be the 4 by 4 identity submatrix. There you have it. This should, in principle, be a single error correcting code. What's one way that we can use to prove that? Prove that this corrects at least one error. So how do we prove that something corrects an error?
How did you get that 4 by 4 matrix?
What 4 by 4?
The P?
P?
Yeah.
This is it here. So it's not 4 by 4, it's actually 4 by 3. So I just took that straight out of here. This is 4 by 3. It's the same matrix. Unless I made a mistake. No, it's the same. Okay, well, how about we calculate Dmin? In order to calculate Dmin, easiest way, this is a linear block code. Let's calculate the minimum Hamming weight. Minimum Hamming weight code word. So how many code words do we have here? K is 4, so how many code words? 2 to the 4 is 16. So I'm going to put M here and C over here. So there's 16, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 0, 0, 1. This will be enough to make my point. So all 0 goes to what code word? That's the all 0 code word. 0, 0, 0, 1, if I matrix multiply, this row gets multiplied by 0, this row gets multiplied by 0, this row gets multiplied by 0, this row gets multiplied by 1. So I just pick off the last row. Here, this row gets multiplied by 0, this row gets multiplied by 0, this by 1, and this by 0, so this picks off the second last row. Here, this row gets multiplied by 0, this row gets multiplied by 0, this by 1, and this by 1, so it's the mod 2 sum of the bottom two rows. So I have 0, 0, 1, 1, 1, 1, 0. Here I pick off the second row, so that's 0, 1, 0, 0, 1, 1, 0. Here I take the mod 2 sum of the second row and the fourth row, so that's 0, 1, 1, 1, 0, 1. Here I take the mod 2 sum of these two rows, 0, 1, 1, 0, 0, 1, 1, and so on. So you can continue this for all the code words. Let's stop there. In order to show this rigorously, you'd have to keep going through all the code words, but let's just stop there. You can do the rest on your own, but let's see what the Hamming weight is